We're going to bust out some more I's here, okay? What we've done up to this point are rods, and then if we curl rod into a circle, we would get hollow circles, and if the circle gets taller, we have solid or hollow cylinders. Now what I'm going to talk about is what if I take a hollow ring, turn it into a solid disc, a solid cylinder, or if I take this and give it some height, now I have a solid cylinder. Okay, so it'll be solid discs instead of rings or hoops, and solid cylinders. Okay, all right, now the thing to remember, if it's solid, we're going to change our strategery than when it was hollow. Okay, when it was hollow, we went around the circumference. We're not going to do that when it's solid. What we're going to do is start at the center, and we're going to work our way outward from the center, adding up progressively larger and larger circumferences until we can recreate the whole thing. All right, what that means is this is obviously a solid cylinder, or I'm sorry, just a solid disc. What if I wanted to take the advice of the Rolling Stones and paint it black? What I could do with this Sharpie to illustrate what I'm referencing us to do is I'm going to start in the middle. I'm going to put a dot. That is now our axis of rotation. Okay, that's where we're at. Now what I could do to turn this whole thing black is I could take this and just make a progressively bigger circle, one thickness of the Sharpie, and then do it again. Make another circle there, just slightly bigger, one thickness of the Sharpie. And then I could keep going and add another circle that is one thickness of the Sharpie. And you see how, sure enough, that circle is getting bigger and bigger, one Sharpie thickness at a time. And if I keep going and keep making circles, circumferences, those circles will progressively get bigger, and their radius will go from a radius of 0 to a radius of r. All right, so just the thickness of that Sharpie pen is our differential quantity that we will be dealing with. Another way I have students visualize it is, I play a lot of records, and so you know what records look like. I'll show you, but this is one from 1981, kids, a band called The Tubes, which you may or may not have heard of, but I'll tell you why I chose this record for this example anyway. But you can see the grooves on that record, right? The grooves on the record. And the way the needle works is the needle goes out on the edge, and then this sucker rotates. And as it rotates, one groove at a time, ooh, there you can see him, one groove at a time, this thing gets progressively closer from the center inward, all of those little grooves. And so if I add up the thickness of all those little grooves that make complete circles, right, the thickness of each of those individual circles, then I will add up to the whole entire record, the whole entire disc. So please think of it as the grooves on a record, or the layers of ink, one Sharpie thickness at a time, painting that sucker black. All right, so I know that's a lot to explain, but it's hard to visualize. So if this is a solid disc, start with that dot in the center. Add layers of progressively bigger circles. So what I was trying to draw was a little guy, then a progressively bigger R and big R and big R and big R circle. Put them all together. Sure enough, you'll build up to that whole entire item. So what I tried to draw with that red circle is one of those differential pieces of the whole entire disc. All right, think of it as one of the many grooves on a record. Now, this guy is two-dimensional, okay? It's not like a rod or a ring where it was one-dimensional. So we're going to use sigma, not lambda, all right? Sigma is a mass divided by an area, so it's the same thing as a differential mass divided by a differential area. Now that area is going to be the area of one of those grooves on the record. So the area of one of those circles. So what was the area of that particular black ring I just made right there? The area of it is the length times its thickness, the length times the width. The length is its circumference. The width is the thickness of that Sharpie pen ink, or the thickness of one of those grooves, which is a very, very small thickness. That's why that's the differential quantity. So we add up all those little circles from 0 all the way outward to r. Remember the formula we always start with, r squared dm, the integral, and our bounds are from 0 to r. Now please remember that differential mass is a sigma differential area. The differential area is the length times width of one of those grooves on the record. So the length is 2 pi r. The width or thickness is dr. So that's what we are going to set up for this. And so we go put that formula together right there. R squared, there's the sigma. The differential area is 2 pi r dr. Now, fish out all of those constants. Everything that stays the same, well, the sigma stays the same. 2 is 2, and pi is delicious. So from 0 to r, we're left with a little r cubed times the differential radius. Okay, I didn't turn that little r into a big R yet. Okay, so all we're integrating is r to the third. That's it. That's easy. It becomes an r to the fourth over 4, and you go from 0 up to r, and then all I did was rewrite the stuff out there. Okay, so now we'll put our boundaries in, and it's 2 pi r to the fourth over 4. Okay, that sigma, remember, is a mass divided by an area. Okay, the mass of the whole thing divided by the area of the whole and entire disk. And remember, it is a solid circle. Okay, that's the area of a circle is pi r squared, and if it's the area of the whole thing, it's going to be a pi capital R squared. Okay, ooh, and I forgot to tell you here, when you put those bounds in, that's when the little r becomes a big R. All right, so that little r, or those differential r's, as they get big R and big R and big R, the radius of any one of those individual circles is the little r. And as you put your bounds in, you're going to go from a little r of 0 to a little r of big R. All right. Anywho, then you what is written in red there is the mass divided by the area, pi r squared. That's what is sigma, m over pi r squared. And then the 2 pi is that 2 pi r to the fourth over 4. Okay, so that is the integral there. We're going to go ahead and kill what needs killing. And it is 1/2 mr squared. Okay, please remember that. Solid disks or solid cylinders have half of the resistance to rotation as a hollow one. Okay, because remember, the hollow one has all of its mass way on the outside, so the mass is far away. So that's a bigger I, a bigger resistance to rotation. A solid item has its mass closer to the axis of rotation, which means it is easier to get it to rotate. It's more likely to accelerate downhill. And you guys remember the video I did the other day with these two cylinders, or this one is a hollow one, this one is a solid one. They have the same radius and they have the same mass, and when they rolled downhill, this one got to the bottom of the hill first because it is more easily accelerated rotationally. This one lagged behind a little bit. And once it got to the bottom and the carpet started to stop them, this one stopped more quickly than this one, or sooner and less distance, because this one is easier to start. It's also going to be easier to stop. Okay, that's what resistance to change means, if it's easier or harder to do so. Okay, now what if that cylinder or disc becomes a cylinder? What if the record becomes a stack of records? What if I take this turn it into one of these, but then it's got some height to it, okay? So this is a solid cylinder that could be added up of a whole bunch of those. Just keep stacking them. You'll notice a very similar trend. It's going to be the same as what we just did. Just add an H. Just add the letter H to it. That's all you got to do. So there's the H, the height of the solid cylinder. There's its radius. The axis, again, is through the center. What I try to draw with that red is, again, one of those differential pieces of the whole thing, starting from the center going outward. So we're, instead of adding up individual pieces of ink, we're going to get progressively larger and larger shells. Another way to think about it is when they manufacture toilet paper, right? This thing is initially empty, but they wind the heck out of it. And as each individual layer of toilet paper gets added to it, it gets thicker and thicker and thicker. And so each one individual layer is what we're going to add up. Think of one layer from the center outward, okay? One layer of paper towels on a roll. So this is three-dimensional now, so it's a density. It's a mass divided by a volume, which means it's a differential mass divided by a differential volume. A volume is 3 dimensions, okay? It's got a length, a width, and a height. The length is however long that circumference is. The width is that differential thickness, a very, very thin strip of paper. The height is however tall the cylinder is. So if you add up all those layers from a radius of 0 out to a radius of r, so remember it's r squared dm, that formula right there. Remember the differential mass is the density times the differential volume, and that differential volume is what I just have written up there. It's 2 pi r times h times the differential radius, okay? That's what we set up to do this. That's what this whole equation is down here, all of that put together. Now, we can fish out some constants, can't we? Look at all the stuff that don't change. The density to the pi and the h. The density to the pi and the h. So all we're now integrating from 0 to big R is r cubed. All right, that's easy. All we're doing is integrating r cubed dr. It becomes r to the 4th over 4 with a capital R up there and an r and a 0 down there. So can you tell this is exactly the same as the thin disk that we started out in r to the 4th over, or integrating an r to the 3rd, that becomes an r to the 4th over 4. The only difference is that sigma is now a rho, and we've added an h. That's all you do, just add an h. The sigma becomes a rho, and you add an h. Okay, so that r to the 3rd becomes r to the 4th over 4. Put the bounds in, and you get this. Remember, the density is the mass divided by the volume. This is the volume of the whole entire cylinder, which is pi r squared. That's the area of the circle times height. There's your 3rd dimension to get the volume, to get the whole thing. So everything that's written in red is that times 2 pi h r to the 4th over 4. And so if we kill what needs killing, what you end up seeing is the I is 1/2 mr squared. That's it. It's the same. It's the exact same I. So it doesn't matter if it's one of these lids, or if it's 2 of these lids, or if I got a stack of these lids. I mean, it doesn't matter how thick they are. An entire cylinder, if it's a solid cylinder, it has half of the inertia as a hollow cylinder. So that's, again, it's the same. This behaves exactly the same. All right. And so with that, I will then remind you of the tubes record, and I will say that it's a kind of a transition. If I told you, I don't know, but they're right in 1981. It was the end of the 70s. You can hear hints of the 80s beginning on this particular record, but the song 1, side 1, if you can read it, I don't know, but what it says is, "I'll talk to you later." Yay, physics.